Today I want to talk about one of the most important concepts in chemistry. And I say that a lot, and I get excited about a lot of different concepts in chemistry, but equilibrium is really one of the foundational ideas in chemistry. And so I want to talk a little bit and introduce a little bit about equilibrium in the context of phase changes, first of all, and then in solutions, kind of second of all. So dynamic equilibrium, let's set it up first. If I have a pot of water here, so let's say I have liquid water here, so H2O in the liquid phase that's in my pot. As I increase the temperature, so here's my heating element, if I increase the temperature to 100 degrees Celsius, right, then that's going to cause the water to boil. And we know that boiling water happens because there's these little pockets of gas that form because of the pressure from all of these water molecules going from the liquid to the gas phase, and then they exert this pressure and create these little pockets, and these pockets then kind of rise up to the surface because they are now less dense than the water around them. And then if my pot is open to the air, which in this case it is, then the steam leaves. And so I didn't split the water into its component pieces. It's still water. It's a phase change, but it's in the gas phase instead of the liquid phase. So now we have water molecules that are leaving. We have water molecules that are in the liquid phase that are getting heated up and kind of maneuvering around. Okay, so this is what happens when we have boiling. If I was to make this into a closed system, so if I take this pot and now I'm going to put a lid on it. Let's put a lid on my pot with a nice little handle. So I safely put the lid on the pot there. That's pretty good. So if I put a lid on this pot, then the lid now creates what is called a closed system. So a system in scientific kind of terms is anything that we're studying. So if I'm studying this entire system and it's closed, then that means everything within this I'm going to consider part of my system. Everything around my pot of boiling water here I'm going to consider my surroundings. And this interaction between the system and its surroundings is a really important feature for kind of understanding the chemistry of what's going on. So let's think about our closed system here. If we're thinking about this phase change going from the liquid to the gas phase, so if I have my H2O in the liquid form going to the gas phase, so I heated it up, right? So I heated it up to 100 degrees Celsius, so I increased the temperature, and the liquid goes to a gas phase. Then that's going to happen at a specific rate, and we call that phase change, of course, evaporation or vaporization of my water. So we have evaporation that's occurring at 100 degrees Celsius. Now, if we were thinking about it from another perspective, right, this gas particles, as they reach the top of my lid in this closed system, are then going to, once they're removed enough from the heating element, they're going to start to condense, right? We're going to have liquid water on the surface of my pot here. We see that as steam, right? The steam is the water vapor, but then as it starts to condense, then the water particles are going to go together, closer together, and they're going to go back down into solution. So while my liquid water particles are going into the gas phase, these gas phase particles then are going back into the liquid phase. So we could kind of think about that as the temperature cools back down to 100 degrees Celsius, then the water goes from the gas phase to the liquid phase. And we would call that, again, condensation. So both of these processes are happening simultaneously in my closed system because it's a closed system. If I take that lid off, then it's no longer a closed system. As long as I'm keeping it in a closed system, I'm not messing with the temperature, then at this particular temperature, both of these reactions are going to be occurring. And they're going to get to a point, and you could probably kind of intuitively understand this, they're going to get to the point where the rate of this reaction, going from a liquid to a gas, is going to be equal to the rate of this reaction going from the gas to a liquid. And so we can write this all as one step where my arrows are reversible. So I'm going from the liquid to the gas phase, and I'm also going from the gas phase to the liquid phase, and this is occurring at a specific temperature. Now we call this process with these reversible arrows, we call this equilibrium and dynamic equilibrium. equilibrium is used in kind of common speech to mean balance. Like if you're regaining your equilibrium, then you're regaining your balance. And that's kind of a good way of thinking about things. We like balance in chemistry. Dynamic equilibrium, though, is really talking about a chemical process in which the rate of the forward reaction which we define as the traditional way that we've talked about chemical reactions is going from reactants to products, is equal to the rate of the reverse reaction, which we define as going in the opposite direction. That would be products then to reactants. So the liquid going to the gas phase is happening at a specific rate, and the gas phase is going to the liquid phase at a specific rate. When those two rates are equal to each other, then we call that dynamic equilibrium. And we have to keep this temperature the same, because otherwise temperature is going to impact how fast something happens. We know there's a correlation between temperature and the movement and speed of particles, so that would have to be kept constant in order to make this true. So dynamic equilibrium. These reversible arrows then are going to indicate equilibrium. And again, forward reaction, reactants to products, reverse reaction, products to reactants. Okay, I like to think about dynamic equilibrium as sort of a, I always kind of picture it as a Bugs Bunny, Elmer Fudd kind of action. So if I have Bugs Bunny here that's digging a hole. So here's my shovel. That's pretty good. This is a good shovel. Actually looks like a spade in cards, which, you know, that's based on a spade, which is a shovel. So here's my shovel and I'm digging a hole. And if I'm digging the hole, and here's my dirt, and it's going in a pile here. Here's my pile of dirt. This is a very excellent drawing, as you can see. All right, so we're digging from the hole and we're putting it into the pile. And then if simultaneously someone comes up and they are digging, and they have maybe a better looking shovel, because I'm doing it the second time around, and they're digging from the pile and they're putting it back into the hole. So that's the reason I always think kind of Bugs Bunny, Elmer Fudd. So Bugs Bunny is trying to do something, trying to accomplish something, digging the hole and creating a bigger hole. Elmer Fudd is coming along and trying to thwart that, and he's trying to put the dirt back into the hole, right? So one person is moving the dirt this way, the other person is moving the dirt back. If one is moving faster than the other, then this hole is going to get bigger, right? So if Bugs Bunny here is digging the hole and he's moving faster than Elmer Fudd, then this hole gets larger. If Elmer Fudd is moving faster than Bugs Bunny and refilling that hole, then that means the hole is getting smaller. But if both Bugs Bunny and Elmer Fudd are digging at the same rate, right, as each other, that even though dirt is moving back and forth, they're happening at the same rate, and the size of the hole remains the same. So the concentrations at equilibrium then are going to stay the same of both my pile of dirt and the dirt that's in the hole. So that's kind of a key feature here, is that the rates are the same and that the process is ongoing. That's where the dynamic part is. So both reactions are happening simultaneously. Which we'll just capture with the reactions are ongoing and simultaneous. So both the forward and reverse reactions are occurring. They're just occurring at the same rate. So dynamic just means change in general. So we're changing something about a process, but we're doing so in a balanced way. And that balance comes from these equal rates. Now, if we think about solutions chemistry, get rid of that terrible drawing. If we think about solutions chemistry, we know that solutions are made up of two parts, right? A solute and a solvent. So the solute is the thing that we're dissolving, and the solvent is the thing that we're dissolving into. So just a little review of kind of our phase change stuff as well as the solution stuff. So we have kind of the substance dissolved and the substance dissolved into. So if we picture a beaker here, and let's say that we have sodium chloride, which is our table salt, as a solute, and we'll have liquid water as our solvent. So we're going to put our sodium chloride into solution. And sodium chloride is an electrolyte. It actually splits into its component pieces. It's soluble in the water. So it doesn't stay as sodium chloride. It splits into or dissociates into its component ions. And it's because of the interaction with water that it does that. The water molecules, because they're polar, like to split apart and surround these different ions. Okay, so I have these ions that are in solution, and they're attracted to the water molecules. So if we kind of take some of this sort of out of the context of my solution here, so we'll draw a little bit more here. If I have a sodium ion, and I know my water molecules are bent and polar, because they have that tetrahedral geometry, and oxygen, which is more electronegative, has a slight negative charge on it. These hydrogens have slight positive charges on it, so one side is negative, one side is positive. That slight negative charge and this positively charged ion are going to be attracted to each other. This is called ion dipole attraction. It's an intermolecular force, an IMF, that is an attraction between a polar molecule and an ion. So all of my water molecules then are going to go around and surround this sodium atom in such a way to where the oxygens are the ones that are the closest to the ion. And in separating these ions and splitting them apart, then now my sodium is surrounded, and so too are my chlorides, except my chlorides are going to be surrounded by the opposite side of my water molecules. The positively charged, partially positively charged hydrogens are going to be surrounding the chlorides. So we call this hydration energy. There's an attraction between the ion and the water molecules, but at the same time, there's still attraction between the positively charged ions and the negatively charged ions. That's how they got together in the first place, is that attraction between opposite charges. So there's a balance then in solution of the attraction between the ions to each other and the attraction between ions and the water. So there's really two processes that are occurring when something dissolves. My solid sodium chloride here is going into solution. So I have sodium ions that are in the aqueous or aqueous form now. And at the same time, my ions then are attracted to each other and are reforming that compound. Now, kind of depending on how attracted they are, so depending on the charges, depending on the attraction, these strengths and the rates of these processes are going to be slightly different. For sodium chloride, for example, sodium chloride is very attracted to water, so it's going to stay pretty soluble, but both are still happening simultaneously. We're putting solute into solution, we're dissolving, and then we're coming out of solution as well. We call this dissolution. So this would be solution, the forming of ions into their solution, and this would be dissolution, where the ions are coming back out of solution. You could think about it as precipitation also, although precipitation is really the term that we use when you have a fairly insoluble solid. But for a solution, the solution and the dissolution are going to raise or reach a certain rate, and the rate to that is going to be defined by a constant that we'll talk about later. But we can kind of combine these guys together then into an equilibrium process. And we know that it's equilibrium because of these reversible arrows. So the rate of the forward reaction becomes equal to the rate of the reverse reaction, and at some point there's a balance between these two forces where my solid is going to dissolve in as much as it can, these guys are going to come out of solution, and meanwhile they're both still happening simultaneously. This is a dynamic equilibrium. For most chemical processes, they can reach a point of equilibrium, and most chemical processes can be written in this way. When we write a reaction from reactants to products with just a forward reaction arrow, then we're usually just indicating that that's really the preference. When we end up doing this, when it reaches equilibrium, mostly what we have are these products anyway. So that's really just kind of a shorthand notation to showing which side has a preference. If there's really more of an equal preference between the two, which is not the case in this particular dissolution reaction, by the way, but if there is a preference for it, then we would probably just write it with an arrow